Hi there, it's Mr. Wiedemann. Whoa, there I am. That's what I look like, in case you've forgotten. Welcome to our very first video in AP Physics together. I will be your host as we explore the cosmos together. Anyways, we have been discussing and learning about Newton's law of gravity, a fact that all objects in the universe are gravitationally attracted to each other, and that this attraction sometimes means some objects are bound together, like us and the Earth right now, like the Earth bound gravitationally to the sun in a perpetual orbit. But it seems that perhaps we can change that. We can change how much we are bound to something. And Newton, in fact, imagined us breaking our bonds from this terrestrial home and venturing out into those cosmos that you see before you. Represented two-dimensionally with a yellow sun in the center and all those planets, definitely not to scale. But before we dive into this, let me remind you of what I would like you to do while watching. 1, I want you to take notes. If you would prefer to take notes on your iPad, watch this video on another device while taking notes, a computer or your phone. Or you could take notes on paper, and if you really wanted them in Notability anyway, take a picture of them. But I want you taking notes, please. This is your responsibility to do so. Number 2, when I ask you to pause and try a problem, do so. I mean it. It is by design that I want you to try a problem there. Don't be afraid. If you can't get it, that is okay. The solution is coming right up. Please give it an honest try. Also, remember you can pause, rewatch, and watch this video later to review. Alright, so Newton's famous thought experiment goes a little bit like this. Imagine our world without any air, so there's no air resistance at all, and perhaps a cannon atop a mountain, and it fires a cannonball. That cannonball, of course, falls to the earth, bound by the pull of Earth's gravity, locked in the gravitational field that emanates from all the mass of the Earth. Note, though, that if the Earth were flat, the cannonball would hit the ground just as soon as a cannonball perhaps dropped from the top of that mountain would hit the ground, like our bullet shot versus dropped experiment. But Newton imagined perhaps if this cannonball were fired with a little bit more velocity, it could go even farther before hitting the surface of Earth. And I think some of you guys know where I'm headed with this, but if you were to fire the cannonball with enough speed that it could fall around the Earth indefinitely, that it would just fall and fall and fall, and the Earth would perpetually curve underneath it, and both of those falling and the Earth curving underneath would be at the same rate. Now, Newton might have taken this next step in thinking, well, what if you fired even faster? That orbit, perhaps it wouldn't be circular, but it might be elliptical. Or, what if you fired so fast, perhaps that cannonball would never come back? But let's look at that situation with that circular orbit. How fast would the cannonball have to be going in order to orbit the Earth close to the surface? All right, let's imagine that circular orbit around Earth. We've got our cannonball going around the Earth, and we're going to assume this is really close to the surface of Earth. So we've got an object in circular motion, radius r. Hey, we've seen this before. We know what forces are necessary to make an object move in a circle, and we've called that sum of forces causing an object to move in a circle centripetal force. And the force responsible for this circular motion? The force of gravity. So, got mass times our centripetal acceleration is equal to our force of gravity equation, our big G, our universal gravitational constant, times the mass of the Earth, times the mass of our cannonball, divided by the radius squared. Notice on both sides of the equation here, we have the mass of the cannonball. It's the lowercase m, right? The mass where there is a centripetal acceleration of that mass, and the mass of the cannonball being gravitationally attracted by the mass of the Earth. Of course, we can cancel this mass out. We also see that our centripetal acceleration is equal to v squared over r. I hope you remember. So we can set up our equation and notice perhaps something else cancels out as well. This radius on the left-hand side and this radius on the right-hand side are the same radius. The radius of the object's circle, and the radius here is the distance between the cannonball and the center of the Earth. So that radius as well can cancel out on the left-hand side, and we're left with 1 on the right-hand side. So our speed, our velocity for our object in orbit is equal to the square root of our universal gravitational constant, the mass of the Earth, divided by the radius. This, of course, is the tangential speed at any point, and this equation also, notice, it doesn't depend on the mass of our cannonball. It only depends on the mass of the object being orbited. This is an important distinction. It only depends on the mass of the object being orbited. This equation is not on the equation sheet, but it would still be useful to memorize. But we haven't completed our problem yet. We still want to find out how fast this cannonball would be moving if it were close to the surface of Earth. So to solve this problem, we need the mass of the Earth and the radius of this orbit. And we're saying it's pretty close to the surface of Earth, so we'll take the radius of the Earth. But where are we going to find these things? Oh, well, it's not that hard. It's going to be in Appendix E of your book. I repeat, Appendix E. I would totally bookmark that. So I would like you to pause the video, find those constants, the mass of Earth, radius of Earth, and calculate the speed for this orbit and see if it matches up with my calculation that I will show you here in just one moment. I got 7,906 meters per second. Make sure you get that as well. Also, note how the bigger the radius, the lower the orbital velocity. So the further away you get away from the Earth, the lower velocity required, which makes sense with Kepler's laws. All right, so what is the orbital speed of the International Space Station? The ISS happens to orbit 250 kilometers above the surface of Earth. So with that information, I'd like you to find the orbital speed. So try that right now. Try it yourself. Right now. Seriously. Stop the video. Do it yourself. I will not continue until you do it. Really? Have you still not paused the video and tried it? Come on. Do it. I'll know if you don't. All right, so the trick here is to remember that that altitude above the surface has to be added to the radius of the Earth. Plug it into the equation, and I got about 7,756 meters per second. I hope you did too. Thanks a lot for trying that. Another natural question that you might ask about this speeding bullet of an International Space Station orbiting around the Earth so close to its surface, 7,700 meters per second. That is 77 football fields in a second. Zippity zip zip. how long would it take it to orbit the Earth? So really what we're asking for here is, what is the orbital period? And I'm going to remind you of an equation that we derived a while ago when we proved Kepler right, when Newton proved Kepler right. And I'll write it here. So if you don't remember how we got this, I encourage you to look back at your notes and see that. But here, we've got the relationship between the period of an object's orbit squared divided by the radius, or the average distance from what it's orbiting, cubed, is equal to some constant, 4 pi squared over the gravitational constant times the mass of the object being orbited. So while this equation is not on your equation sheet, it might be a useful one to memorize, or at least know how to derive. All right, so pause here, take a moment to use this equation to find out how long it'll take the ISS to orbit the Earth once. I got 5,363 seconds, or about 1.5 hours, meaning that the astronauts on the International Space Station every 1.5 hours see a sunset and a sunrise. Pretty cool. All right, what is a geosynchronous orbit? Now, before we dive into this, I've been struck by a desire to reflect. 250 years ago, an English dude had a thought experiment, and now we have 8,000 satellites orbiting our planet, delivering the conveniences and luxuries of GPS, radio, television, almost instantaneous communications over the entire globe. What? Okay, back to your regularly scheduled content delivery method. A geosynchronous orbit means it is a satellite's orbit is synchronized with the Earth. Well, okay, Mr. Wiedemann, you might say. Go on. Meaning, as the Earth rotates on its axis once every 24 hours, the satellite up in the sky also completes one revolution in 24 hours. Just means that relative to the surface of Earth, the satellite doesn't move. So whereas satellites close to the surface, like the International Space Station, move across the sky, and we can see that motion. Some of you may have already seen in the night sky, you'll see a satellite every once in a while. These satellites appear to remain still, I did air quotes there, still in the night sky, in the day sky. It's up there. So, let's find out the altitude of such an orbit. An orbit with a period of 24 hours. I'd like you to pause here and figure out that altitude. Then I'll show you how. So the radius of this orbit would have to be 4.22 times 10 to the 7th meters. But the altitude, or the distance above the surface of the Earth, of course, would just be this minus the radius of Earth. So 3.6 times 10 to the 7th meters above the surface of Earth. All right, I have a couple practice problems here for you from the book, so I'd like you to try them, and in just a moment I will show you the solution. But please, 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 please try them before I show you that solution. So pause here. All right, so I got the altitude to be 1.7 million meters. Now find the speed of a satellite in geosynchronous orbit. And I got 3,072 meters per second. All right, you have a few other problems in the book for practice that are listed on the schedule. And a brief reminder that you have an assignment due for me on Monday.